Hi, everyone. Welcome to Modular Headquarters and to the kickoff of Modular Hack Weekend. We're so excited to have you here with us tonight, whether that's in person or tuning in online. If you haven't already, grab some food, find a seat, settle in, get connected to the Wi-Fi. There should be a bunch of different pieces of paper spread around the room with the network name and the password. To everyone on the live stream, thank you so much for joining us remotely. We've got an awesome lineup of talks and a hands-on GPU programming workshop coming up, so let's jump right in. So quick reminder, if you're sharing photos or updates at all on social media tonight or during this weekend's hackathon, please use hashtag modular hackathon so that we can repost you and amplify your posts. Huge thank you to our speakers tonight, Jared Roesch from NVIDIA, Chuan Li from Lambda, Bin Bao from Meta and GPU Mode, and our very own Chris Lattner, Chris Hodge, and Brad Larson. And of course, tonight's event and Modular Hack Weekend wouldn't be possible without our amazing sponsors, NVIDIA, Lambda, and GPU Mode. Thank you so much. So super quick agenda for tonight. We'll start with 4 lightning talks from Chuan, Bin, Jared, and Chris before we transition into the GPU programming workshop. After the workshop, we'll open it up for mingling, working on your hackathon projects, and just hanging out. So without further ado, finally, I'm going to kick it off. I'm going to kick off tonight's lightning talks and hand it over to Chuan Li, who is a founding team member and chief scientific officer at Lambda.
Check. Good. All right, thanks a lot. So I'm Chuan from Lambda. Today I'm going to talk about how to solve 2D puzzles with small LLMs. This is a work of David Hartman, who is a researcher at Lambda, and his friend Jan and Daniel, who are both PhD students from University of Mainz. They three actually was the team that won last year's OctoAI challenge. So let me see if I can. Yeah, if you are not familiar with the OctoAI challenge, don't worry, I'm going to talk about it in a bit. I'm also going to talk about how some of the community's best practice of tackling these kind of problems, and also what our team did differently to win the competition. Just like for the record, we are not code engineer, we are not compiler engineer, so we didn't do any low-level like kernel optimization, but I feel like we are chasing the same goal here in terms of we are trying to solve a challenging problem with less resource. So hopefully this talk gives you guys a slightly different perspective. All right. So what is the ArcAGI? Arc stands for Abstract and Reasoning Corpus. Intuitively, you can think of ArcAGI is sort of like an IQ test for AI. Here's an example. Basically, you are asked to solve some 2D puzzles. In this case, you are given some like examples. In the first 3 columns give you the input and output, and then you are asked to generate the output from the first column. In this case, you are supposed to fill in the empty box with yellow. So why this is fun and a challenge? Well, to begin with, there's a lot of like cognitive tasks need to happen here. You need to recognize the pattern. You need to recognize the mapping between the input and output with only a few examples. So that's already challenging enough. And this is also in particularly challenging for LLMs, because you can imagine LLMs works in 1D space. So in order to have LLM work on this kind of problem, you need to flatten the 2D grid. And this flatten operation sort of like messed up some of the spatial relationship between the cells and make it harder for LLM to learn. Also, it's very easy to make the problem much harder by just simply scale up the resolution and also impose some kind of long-range structure, for example, global symmetry. And overall, this task is just very brittle in the sense that everything has to be pixel-wise perfect. If you make one single mistake, the answer is wrong. And on top of that, I think this is most interesting for today's topic, which like the organizer actually imposed a resource limitation during online testing stage. You can only use 2 NVIDIA T4 GPU for 12 hours to run your solution. And this means you cannot run very big models or run the model for a very long time. So to put all the challenges into a context, this is a graph showing the relative performance of AI versus human across different type of tasks. And the yellow curve is the best AI algorithm for ARC. You can see throughout the years, there's definitely some progress, but the progress is at a much slower pace compared to other tasks. Where you see the blue curves basically shows in other tasks, the AI quickly catch up with the human and sometimes even surpass human performance. So what our team did last year is to sort of like bring this yellow curve up to speed. So in the rest of the talk, I'm going to discuss like how we did that. Yeah, before diving into our own method, just want to touch on a few best practice of like how community has been tackling this problem in the past. I'm going to focus on LLM-based approach because this is really popular and this is also something we use. As you can imagine, LLM are not trained for this kind of task. They are trained for natural language task, and this is sort of like a pattern recognition task. So intuitively, you want to collect more data and fine-tune the model. So there's a lot of people doing that. And you can get new data from different sources. You can have like synthetic data, program generated ARC-like problems and answers. You can have data augmentation. But the one thing I want to particularly highlight is this thing called test time training. This is very interesting in the context of ARC challenging because ARC allows you to upload code instead of model weights. So that means during this online testing stage, you can actually run fine-tuning in addition to the final inference. So this gives you the opportunity to basically fine-tune the model weights for individual tasks. You're actually making a separate model for individual tasks. Obviously, this brings more compute, but you got a much better model performance on these tasks. So if you do all this fine-tuning with data from different sources with some engineering trick I'm going to mention later, you're actually able to improve the performance from the baseline below like 20 points to about 40 points. So that's actually pretty good, but we still need another 20 to 30 points improvement to win the competition. So what did we do? Well, this is something we did not do. We did not do prompt engineering. We did not do chain of thought because we just asked LLM to do next token prediction straight out of box for the answer. And we cannot afford running large model. The first thing we did is to try to optimize the efficiency across the board. And the biggest change we made is actually remove most of the token from the vocabulary. We removed 99.95% of token from the dictionary, only keep 64 tokens. And this does not only reduce the memory requirement to run the model, but also helps the model to focus on this kind of puzzle-solving pattern recognition task instead of thinking this is a language task. And this is an example of how to represent the 2D grid puzzle by the remaining 64 type of different tokens. We have numbers to represent the different colors. We have special tokens for the beginning of a sentence, end of a sentence. And we also have a special token to separate input from output and do the new line switch. We also did a very aggressive quantization with 4 bits for the weights, with quantized LoRa for fine-tuning, and we use gradient checkpointing. So all these reduce the memory requirement, so we can actually run test time training during the submission. And we also use like Unsloth as the fine-tune library. Big shout to Unsloth. So with all this engineering trick together with fine-tuning, gave us the sort of like from 20% to 40% improvement. However, as I said, we still need to get another 20 to 30% to win the competition. So what did we do? The big lesson learned here is we just need to accept like LM can make a mistake and will make mistakes. Just think about it. Like the best model we had back then gave us 40% accuracy. That means LM will more likely to give you a wrong answer than the right answer. So let's say just accept the fact. So how about let's just like LM roll out more potential answers. So there's a higher chance to have some of the answers being correct, and try to spend more time to look at the answers and pick the right one. And what we find along the way is, despite LM being a mediocre generator for the answers, it actually can do a very decent job as a discriminator. then it tells the good answer from the bad answer. So how do we it seems stuck. Is there a way I can go to the next slide? Yeah, it's not. Okay, cool, thanks. Yeah, so how do we implement this? First, we need to get a bunch of proposals for the correct answers. What we did is depth first search, try to enumerate all the possible 2D patterns. But I was joking, that would be so expensive. So what we did is we try to do early stop. While we are generating a hypothesis, we try to score the sequence generated so far. And if the score falls below a certain threshold, we do early stop. We skip the rest of the subtree and switch to a different branch. But the trick thing here is how do we score a potential answer on the fly? Well, the answer is actually we can use the joint conditional likelihood of all the previous generated tokens to use that as a score. This is basically output of LLM. So we actually use LLM not only as a generator, but also as a scorer. And if we do that, we are able to quickly prune the tree search and find a set of very promising candidates for the answer. Now, the question is, we have this set of candidates. How can we choose the best one? Yeah, the lowest hanging fruit is just like pick the one with the highest score. But that actually is not going to be optimal. The thing about this, we actually give LLM a degenerated version of the original question. We flatten the 2D grid into 1D, and it depends on how you flatten the 2D grid. It can be row-based or column-based. The order of the token in the output is going to be different. That will give you different scores. So we think, why not just do data augmentation on both the input and output? So let the LLM look at the question and answer from different perspectives. And for each perspective, you will have a different score. And we sort of aggregate the score from all the perspective. And that gives LLM a more holistic view and give it a better chance to pick the best answer. So this is the key. If we do that, we are able to boost the performance up to 70.1%, which is the final solution that enables us to win the competition. And also want to put this into context. OpenAI released O3 a month later and got a lot of more improvement in terms of score, but also cost 100 times more test time compute. And this tells us two things, basically. First, the field just moves so fast, it's crazy. But at the same time, there's a huge amount of opportunity to basically optimize the effectiveness and efficiency of open source models for very specific tasks. Yeah, to wrap things up, I guess this is a really interesting study that we learned a few things. First of all, it's kind of actually amazing to think LLM can actually do this, given all the challenges and the limitations. But also, we learned that in order for LLM actually to do those jobs, you have to augment it with engineering improvement, make everything more efficient, and try to leverage LLM not only as a generator, but also as a discriminator. Things like give LLM a lot of different perspective to see the problem as a whole. So all this says LLM need to be optimized or can be optimized for very specific questions. And yeah, here's a link that can give you more details of the work, including a research paper, the code, and the pre-trained models. And feel free to reach out. Happy to discuss more in details. And yeah, thanks a lot for listening. Enjoying the workshop, enjoying the hackathon.
Thank you so much, Chuan. Next up, we're bringing in Bin Bao, who is joining us virtually via Zoom. Bin is a software engineer at Meta, and he is the tech lead on torch.compile. And tonight, he's giving us a sneak preview into new work on running PyTorch inference without Python.
Thanks, Caroline. Let me start sharing my screen. Can you guys all hear me?
Yes, we can hear you great.
Okay. Can you all see my screen?
Your slides.
You can see my slides, right?
Yes.
Okay, cool. So, hi everyone. I'm Bimba from PyTorch compiler team at Meta. So it's my pleasure to share some of our recent work with the audience in this workshop. So the title is like from PyTorch models to standalone binaries, right? Let me explain a little bit by starting with this question, like how fast can you deploy a PyTorch model? So the context, I think that probably we need more context and get aligned on what I really mean by this. So let's suppose you have a computer, right, that has, NVIDIA GPU, and you already have the operating system, let's say Linux, and also CUDA library installed on your computer. Then what is the faster way to get a PyTorch model running, right? We all know like PyTorch is your model is written in Python. So which means you probably need to download and install some virtual environments. And also after that, you have to install Python, you have to install PyTorch, and maybe some other third-party libraries. Right. And then somewhere you find these model files in Python, and then obviously you also need model weights. And model weights is like the core of your brain, right? Like those are usually large, but inevitable, you have to download them. So if you look at this flow, right, like, well, let's think about like, what if I say, hey, you don't really need this to download the virtual flow? Like we don't use Python, right? So which means you don't need to download that, you install that. You don't need to download and install these. And instead of giving you model files, let's say I give you a model binary, a single binary that with a binary, you just run it like with. Of course, you still have to download your weights, and then by doing that, you basically can achieve a pretty fast way of quickly get a PyTorch model up and running, right? So obviously, with this approach, there will be minimum dependency. Like you don't even need to install libtorch, like which is a C++ library for PyTorch. And then you will get a very small binary size, right? Like, I shared a screenshot here. Like in my local experiment I have done is I have turned a Llama 3.1 model. Like if you look at the first line of the files, it's basically the binary is 8 megabyte, right? And that's it. And for the weights, it's 8B and with BF16, so it's going to be 16 gigabyte weights. That still, as I said, that still will have to be used, right? Yeah, so basically this will be like kind of a minimum, the quickest way you can get your PyTorch model running. So like what's behind this magic? How can we actually achieve that? So the magic really boils down to this like ahead of time compilation flow in PyTorch 2. I'm not sure like how familiar the audience is with PyTorch 2 compiler stack, but for the regular PyTorch like 2 stack, then what you have is we call the JIT compilation, right? Which is basically the upper part of this graph. Like for this flow, then we have something called Torch Dynamo as a kind of like a front end to your compiler. That's a way to capture a graph from your model code. And then that model code is fed into something called Torch Inductor. Also, I can call it JIT Inductor here. And that will kind of optimize your program and turn them into Python kernels, which will be further lowered to run on your GPU. And for our non-kernels part, there we also will generate Python code as Python wrapper code, kind of managing the kernels and managing data. I will have some simple examples show what I mean here. But essentially, like the upper half is how the regular PyTorch 2 compiler flow looks like. If you use torch.compile in your code, that is what's happening under the hood, right? The lower half really shows like instead of doing that, we actually can do ahead of time compilation, right? So now with the front end, we use torch compile. That is a ahead of time way to export your program into a single graph. And that graph will be fed into a special mode of inductor, torch inductor, which is called AOT inductor. That will, again, it will generate Trident kernels, but then it will further compile that down to cubing files, which is like the kernel binaries for NVIDIA GPUs. And then for the wrapper code, we will generate a C++ code instead. And then these with plus weights and some like metadata information will be packaged into a .pt2 file, and we have utilities to actually run this in the native world. Right. Let me show this very simple example. To give you a rough idea like how that AOT compile look like. And suppose you have this very simple model, right? Like it has this artificial forward function, and it calls sine operation first, and then multiple. Then there's a cosine operation. Right? So that's the Python code, PyTorch code. Then after you run the torch compile, right? Like if you run torch compile, I highly recommend you use this like torch_logs equals to output code to see what actually our compiler generates for your both the kernel code and the wrapper code. And in this case, let's say for the first sine operation, we will generate Trident kernel for this. And roughly looks like this. And then if you look at the generated Python code, right? So I have highlighted a few like functionality here, like to tell you what our wrapper will do. For example, it will take care of things like setting the string, CUDA stream. It will allocate intermediate tensor, like here empty threaded, and then it will invoke this Trident sine function like kernel you just saw, right? But then in some other cases, it doesn't always generate Trident kernels. Sometimes it will just call back to what PyTorch eager implements. So we call it fallback ops. For example, here it calls external kernels MN, which calls to the PyTorch implemented multiple. Then also you can do things like reuse your buffer for memory, right? So these are in Triton. Right? If you do the ahead of time compilation, this is in Python. So if you want to do ahead of time compilation, then you cannot do this, right? You just have to do the equivalent for CPP code. So I will quickly go through this. But yeah, once you get the C++ world, mostly you have like one-to-one mapping with those functionality I just mentioned. For example, you have stream setup, you have empty threaded, and you launch a CUDA kernel for the equivalent like Trident kernel generated Tribune files. And then you have like the ways to call back to fallback ops. Again, you can still do the memory management by moving buffers, moving tensors around, right? So this AOT inductor thing is not something like completely new. We started like 2 years ago. It gets pretty like mature over the years. So one thing we did there is we defined a clear small subset, like interface surface that interacts with libtorch. So for example, like if you see like empty threaded here, instead of calling like libtorch version of empty threaded directly through C++, we have provided an isolated C interface to do that for you, so that we can get a stable ADI when we talk about the keep the ADI compatibility for the old models we compiled in the past, right? Because we were able to do this, we have a small, clearly defined C interface. So what you can imagine is, what if, let's say, I provide a smaller, slimmer library than LibTorch that just implements this basic functionalities. All right, then suddenly your generated LTI generated code doesn't have to use like LibTorch for your model to run. Right, that's really what makes this like the previous kind of example I showed you, Llama 3.1 example I showed you, like how you can boil down to like 8 megabytes to get it run. And this is my last slide. This thing is still being actively worked on, and it will come soon. But yeah, just for try to give you a quick idea on this new thing we're kind of excited about. So that's all. Thanks.
Much, Ben. Now we are bringing it back in person with Jared Roesch from NVIDIA. Jared co-founded OctoAI, which was acquired by NVIDIA, and he has spent years building ML systems and GPU infrastructure. Thank you.
Nice to see everybody here to talk a little bit about the CUDA platform here in 2025. So, oh, I forgot I have my arrow keys. There we go. So I think one focus of the CUDA platform that as it's been growing over the last few years, I think often CUDA to most people means CUDA C++. The idea of I'm going to write a low-level C++ program, I'm going to program the GPU in that mechanism. But the way that we think about it is that CUDA is not only CUDA C++. In fact, in the last, let's say, 5 to 10 years, the scope of CUDA as a platform has really grown quite a bit. And the way that we think about CUDA at NVIDIA is not just one component, but it's really our overall platform and a set of things that interoperate and that can be programmed and used in combination to program the GPU. So what that looks like in sort of slide form is in the beginning, and this is sort of the CUDA that people know as MVCC. There's the CUDA runtime, which at the low level deals with allocating memory on the GPU, managing streams of commands, the GPU status, information on power, et cetera, all the sort of low level functionality. Then there's MVCC, which is a C compiler and a set of C extensions that we made that is really what people I often think about CUDA is, that as especially the C++ side of it, where you can write, a normal C++ program, provide a couple annotations, and then map it onto the GPU. And then libraries like cuFFT or cuBLAS, or later on cuDNN. But what's happened actually is that CUDA these days is actually many, many, many things. So we have a series of frameworks and TSLs that we support. We just heard about torch.compile, which builds on some of these layers I'm going to talk about here in a moment. There's SDKs, things like Rapids or BioNeMo. There's a lot of domain-specific work. For example, there's accelerated networking now that people are doing around 5G or cellular infrastructure. There's QQuantum. There are a lot of libraries that actually make it so that you don't have to do a lot of low-level programming like Thrust or, again, the sort of device libraries, like cuBLAS or cuDNN. There's communication libraries like Nickel and so on and so forth, and it keeps building. And what we really see is that all of these pieces need to integrate and interoperate together, and that's a big theme of what we've been building. I think, and most importantly, like we just saw in the last talk, is all the software is layered on top of each other. And what I think makes a lot of it powerful is that you can compose the different pieces that you've built. So for example, PyTorch is actually, today, torch.compile is actually making it a new way to use a different set of these components. But traditionally, PyTorch looked a lot like this, where you have PyTorch invoking something like cuDNN. cuDNN is actually a layer on top of cuBLAS. cuBLAS these days is actually using Cutlass internally. And then Cutlass is in itself a DSL written in CUDA C++, which is then compiled by MVCC and then runs on the CUDA runtime. And we see that this layering is actually very important because it allows people to break into the right abstraction level that they care about. So for example, if you want to write a new kernel, you can go all the way down to CUDA C++ and write it yourself. Actually doing that these days and writing very high performance code is very hard. So Cutlass makes it a little bit easier, but it's still very difficult. But for most people, there's a library that they want to call that implements what they care about, or even more programmers on top, and just write PyTorch directly and never touch any of these lower layers. And it's very rare that one application actually just is using one layer of the stack. I think most importantly, what we've been designing for and we're trying to push the evolution of CUDA forward on is that interoperability between all these components is very seamless, and you can use it in the languages you want to program in and the libraries and abstractions that you care about. I think part of this motivation for us is that we see more and more that optimization is a domain-specific problem. It's very hard to build one toolkit to optimize every program that you care about. For example, in the world that we all live in these days, many of us at least, is a very small subset of the programs that people actually care about. For example, deep learning, you get a recommender system, or you get a graph neural network, or you get a large language model. And these are all neural net style programs, matrix multiplications that have different sets of constraints. Some of them are memory bound, some of them are compute bound, some of them are sparse. But this is still a very small slice of the programs that people care to optimize in the world, and it's not representative of all programs that people care about. For example, a lot of those fit in the deep learning bucket. There's still a bunch of problems in scientific computing that are very interesting. There are lots of challenges in graphics. And furthermore, it's also a hierarchical problem, which I think is why the layers of composition are so important. There are things that are happening, for example, in deep learning at the model scope. There are things that are happening at the operation scope. There are things that are happening at the kernel, and even the individual C++ function that you're writing. And in that world, that's why we believe composition is so important in the layering, because you need these pieces to fit together in order to make it all work. So if you had the ability to write an optimized function for matrix multiplication, but it doesn't fit into, say, warp, which is being used for physics-based rendering and sort of differentiable programming, then you're going to have a challenge. And so actually warp is a great example, which is built on all the layers that I just described about, and actually uses C++ as a code generation target, and then uses all the tools that we just discussed to produce code that runs on the GPU. But the important part that happens with all of these is that the layering builds on foundational abstractions. So for example, part of the reason why this all works is that we have things like ptext at the bottom. And often ptext is viewed as, if you write ptext, you've sort of broken the CUDA platform. But in this layering, we actually view each of these layers as a choice on trading the amount of abstraction you have for the amount of flexibility. Even ptext itself is an abstraction. Actually, the GPU itself has its own instruction set that you can program against. ptext is actually a virtual instruction set that we designed that gives you portability on the programs to run across multiple GPU generations. And so the ability to actually write low-level ptext code is a flexibility that allows people to build their own tools and their own abstractions. For example, Triton, which we just discussed the slide below, actually has its own compilation stack built in MIR that eventually produces LLVM code, which then is lowered via the ptext backend to run on the GPU. Or famously, there's a lot of media sensation around DeepSeek writing their own kernels, but this is actually a point of flexibility, is that the H20 was not optimized in some of the libraries that we discussed, as well as the H200 or the H100, and this gave them the flexibility to write a unique piece of code, and only a small amount of it, without having to rewrite the entire stack, because all those pieces fit together in the abstractions that we built. And most importantly, we're still growing these abstractions. So CUDA is not done yet. There's still a lot of work to go. And one big direction that we've been working on for the last 3 or 4 years is making all of these things work in Python much more effortlessly. So you can see that there's been a big push in both TensorRT and TRT LLM to make it more Python native, make it easier to program. Things like Warp are designed for physics simulation. Some of the new things that were announced at GTC, like the collaboration with Disney and some other physics-based work, is happening directly in Warp. And it's a Python DSL that builds on a lot of the things we just talked about. There's things like CuPyNumeric, which allows you to use all of the numeric libraries that we have built in CUDA directly from Python. There are things like CUDA Parallel or NumbaCUDA, which allow you to write kernels directly in Python, and so on and so forth. And what we're doing is, you can see at each layer of the stack, we're exposing some of these primitives to you, so you can build new things. For example, you can now use all the low-level driver bindings directly in Python and launch kernels or interact with the GPU directly. One really important thrust of this work is actually the ability to write kernels directly. So not just the ability to bind to libraries that we already wrote, but to produce new libraries directly in Python. So you can see some of the boxes here are highlighted. I think the last talk was actually great. You can view torch.compile as a way to author a new kernel. The derived code from compiling your program is effectively a new kernel. There are things like OpenAI Trident that builds on this, Warp, which I just discussed. And then we're also kind of at the lower level, extending it with some new tools. So NumbaCuda, which is a way for you to write classical sort of SIMT style kernels in Python directly. Qtile, which I'm going to talk about here in a moment. And Cutlass just recently released a new Python DSL called QtDSL, which allows you to use all the Cutlass abstractions directly in Python to write kernels. So Qtile is one thing that I want to talk about to close, and Qtile I think is a big extension forward. Qtile itself is the DSL that we're shipping on top of TileIR, which I'll talk about in a moment. And Qtile is one of the biggest, represents sort of the biggest extension to the CUDA programming model. So we've had PTEX for 20 years roughly, but PTEX is very much about the SIMT programming model that we're exposing, where you have low-level hardware threads that are all sharing a single program, and they step forward, and they roughly operate each on a scalar value, and then you write a big parallel program that steps over them. What we're doing is actually extending this low-level abstraction layer of the GPU to now operate on programs that are larger, if you will. So the idea is that you have higher-level threads that compute directly on large tiles of data, and this programming model is both more abstract and also gives us more flexibility to target it to your GPU so that you have portability as you take this program forward, and it's easier to get great performance without having to be as much of an expert. So we'll be shipping this as a DSL, but I think the most important thing, especially for this audience, is the work we're doing in the tile space is actually another abstraction for people who are building compilers or tools themselves outside. So if you want to target generating high performance, dense linear algebra code, you can use this as a back end. And it's another layer in this abstraction that instead of targeting C++, you can actually use this directly to build your own tools. So the IR exposure of this is what we're calling TileIR. And this is a new low-level compiler target, just like PTEX, that you can target directly from a DSL. Our hope is tools like PyTorch or Trident or maybe Mojo will directly emit this code, and it will give them more flexibility in what they do. We're going to be shipping this in the next couple months. It will be exposed as a MYR dialect that you can target, as well as the DSL exposure will be a thin layer that gives you a NumPy-like experience. And I just wanted to highlight some of the CUDA platform extensions that we're up to and the way that we're thinking about this layered approach going forward and giving more flexibility for people to build things on top of NVIDIA hardware. And with that, I'll wrap up.
Thank you so much, Jared. Thank you. Finally, we are thrilled to have Modular's CEO and co-founder, the one and only Chris Lattner, here to join us.
Awesome. Is this working? Is this on? All good? Okay, awesome. Well, welcome everyone. I'm very excited for the folks that could make it in person. Also welcome if you're virtual. We've never done this before, and so I think it's so amazing to experiment with new formats and ideas. Hopefully we can pull more people together and learn from each other. Thank you to the NVIDIA folks and Lambda and everybody for helping. Am I not? I think it started working.
Can you hear us?
Yeah, oh, there you go. Okay. All right, well, I'll start over. So welcome everybody, now that you can hear me. I'm so excited to see you all. Thank you to the people that came and were able to come in person. Also, thank you to everybody that's on the live stream and virtual, and it's amazing to pull people together. We've never done something like this. We've done a hackathon before, but we've never done a hybrid event, and so I think we'll all learn a lot from this experience, and hopefully we'll learn a lot together. And thank you to our sponsors, NVIDIA and Lambda Labs, and everybody who's helping make this all possible. I love, Jared, your talk, and very excited to play with TileIR and MLIR stuff. You know, I'm a huge fan. So today I'll give a quick talk about what we're up to and some of the cool things that we're thinking about. So the briefest backstory you can ever get about Modular, we've been hacking away at something we think is pretty cool for years now. Just earlier this January, we decided, hey, we like this thing. It's actually starting to work. This is very cool, and we started scaling it. And so the cool thing about that is now we can actually open it up and we can tell people about it and we can do really cool stuff. I think if you're following us, we're shipping all the time and adding new capabilities all the time. And so as part of this, we're opening up. And so we're teaching people, we're documenting things finally. And so it's amazing to be able to do this kind of work, and I love it. So why are we doing this though? Like if you take a step back, like why do we care? It's because democratizing compute, I think, is so important. It creates opportunity. It creates opportunity for y'all. It creates opportunity for everybody learning and building and innovating and doing stuff. But the reason I care about that is because it's about the products. It's about building cool experiences. It's not technology for technology's sake. It's because I am a fundamental believer that, like, with the power of all the amazing AI research and algorithms, if we get them into products and we get them in people's hands, we can build amazing and transformative experiences. And so it's this combination of, yes, very nerdy infrastructure like compilers, I represent, but also the research, also the CUDA kernels and the kernel programmers, also the people coming up with new differential equations, which I am capable of understanding, but still struggle with, like, and just like all the people working together in this community is what's really powerful. I'll just give you an example. One example from a couple of days ago, an amazing team, InWorld, just launched one of the world's best speech models. The speech model is really cool because it is super low latency, super low cost. It's much cheaper than the alternatives out there. And it was made possible by two things coming together. In the NVIDIA Blackwell platform, which is a pretty beast mode itself in terms of throughput and performance and latency and all the different capabilities, but then Modular making it go about, their application go about twice as fast. Tim, do you want to say something here? I'm going to put you on the spot for a specific reason.
G'day, everyone. So one of the things, can I borrow the clicker for a sec? We actually want to do is also show a demo, and it'll make sense why I'm doing the demo in a second.
G'day, legends. Super excited to have launched with InWorld, and this is my AI club.
Oh, we lost the audio.
The GPU kernel engineer quit their job. They couldn't handle the constant warp thinking in their life.
So what's awesome about that is, if you hear my accent, this is a one-shot example of this model that served at incredibly low latency. The InWorld team are a group out of DeepMind. They're doing incredible work. They chose our platform because they believe in our mission very much, but they were very excited with the end state results. So this is also a MAX model. And yeah, if you actually go to inworld.ai, you check it out, you can sign up free, get a bunch of credits. We're excited about them. And they're very excited about us too. So this is just one production example. We have many more coming, but we thought we'd share it with you all.
And so, I mean, the cool thing about this is you bring it back to why we do this, right? It's all about applications hitting the market, enabling new things, and making it possible to do that. And okay, so as somebody who cares about systems and compilers and tools and performance and stuff like this, how does that matter? Well, in a speech model, this needs to be real time. Like you're integrating with the speech model, in their case, playing with like gamers, interacting with their backend and things like this. And so by using Max, they're able to get twice the first token latency reduction against systems like VLLM. And so there's a full stack optimization they need to do here with CPU performance and GPU performance and their innovative research and stuff like this. And so this is a fairly transformative thing brought together by two things: the software that MAX and Mojo and all this cool stuff provides, but also the beast mode power of Blackwell. And so this is super cool. We have not yet published the tech report that goes with this. We're hoping it'll be out soon, next week or so. So stay tuned for that. Now, much of AI is open source. I think we can all credit that the open power of the internet and the open power of AI and like things like TensorFlow really catalyzing the open movement in AI. But just because it's open doesn't mean it's great. And so one of the challenges that we all see, and one of the reasons Modular's here, is that this fragmentation and complexity has been slowing down our ecosystem. And just because it's open doesn't mean it actually works, at least not the first time, right? And so meanwhile, software is getting more complicated, but so is the hardware space. And so there's a ton of really cool chips out there. And a lot of great teams that are building these chips. And so the sad reality is that hardware and software come together. And so the reality of our industry is we have this mishmash of different things. They're all, some of them are great and wonderful, but a lot of them are just different and incompatible and weird. And this is a challenge. So, back in my day, there was this really cool meme. It was hilarious. You can still find it on the internet somewhere. And what we thought was we needed a thingy that took all these frameworks and converted them through some magical open source compiler thingy, and then you'd get all the compilers, all this stuff coming out. This is basically what LLVM was for CPUs. And again, back in 2017, I thought that would be cool, but this hasn't worked. It was too early. And honestly, that magic AI compiler thingy, with what I know now, what I know now can't actually work, and it can't actually work for a whole bunch of reasons that I won't bore you with. But now we, as an industry, know this is actually really hard, right? And so what Modular did, and the reason we spent 3 years doing pure research, is tackling this kind of problem, because it is really hard and it's really important. So what are we here to do? We want to crack this problem open. We want to democratize AI compute. We want everybody to innovate and go faster, of course. And so how are we doing that? We're opening up like crazy. And so if you haven't been paying attention, like we started with the Mojo standard library, and yes, strings and arrays are open. We then open source hundreds of thousands of GPU kernels. That's pretty cool. I think we may have one of the most, the biggest open source portable unified kernel libraries that exists, which is pretty amazing. We have 500-600 models, something like that. They're now all open source. We just, this week, Brad, we'll talk about it, I assume, open source the MAX framework and another entire category of things. And we're working on the compiler. And so we want the world's best unified open stack. And this is what we're doing. So if you go thing by thing, I'm not going to go in deep dive because it's not appropriate, but Mojo, again, what we're trying to build is best of. So this is best of not just kernel languages, but best of programming languages. Like, so bring in, yes, borrow checker, ownership lifetime technology that is way nicer to use than Rust and things like this. Yes, bring in the full power of MLIR. Yes, bring in fancy traits and metaprogramming and other capabilities, and bring it in to build the world's best system that can scale, whether you're a Python programmer wanting some code to go fast on a CPU, or better yet, you're a Python programmer who wants something to go fast, and now because it's so easy, you put it on a GPU. And so this is something, and we're seeing this now with folks in the community, I love you all, where you're saying, I'm putting it on a GPU because it was easy. And to me, that is fire. So if you go up to the next level with kernels, again, you can go to Tim's goofy URL, modular/kernels, and you get access to all the open source kernels. And so you can go learn. And so if you're learning how to power these things, if you want to learn how flash attention works, you can go look at the code. Right? And this is production quality, high performance. It's not like a research example. It's like real world code that you can play with. You go up to the framework, again, all open now. You can go look at, like, here's actually production pipelines. And pipelines are not just a forward pass anymore. These are fully KV cache integrated, fancy prefix caching, like all the crazy stuff to deliver state-of-the-art performance. And you can see and work with that and extend and hack and do the next great thing in terms of research. If you go up, pipelines, yeah, so the framework to the pipelines, and so like all this stuff integrated and designed together is really quite powerful. And again, we're starting to see some of the results of this investment and what people can do, because while we're merely infrastructure people, what really matters is the research and the product teams being able to build and innovate and move faster than ever before. So if you haven't followed again, you can just pip install Modular, super easy to work with. It imports and plugs into PyTorch and like all the things that you're used to. We put a lot of energy into making it so it just works, which is really cool. So I'll wrap up by saying, let's democratize AI compute, but this isn't just a compiler problem. This is a people problem. This is a community problem. This is a let's work together problem. Let's build something based on this open collaboration, and let's build something that can scale. And so we think that there's lots of different ways that this happens. We can contribute in some ways in infrastructure pieces. We think that's cool, but let's really shrink this research to production loop. Let's build these next generation experiences that can come together and touch and change people's lives. So I'm very happy that, again, hopefully today we'll all learn and do a lot of cool things. But I'm also happy that other people already are. And so, this is a startup that's using Mojo and building into Max and things like this. And I love hearing the stories of people from their eyes explaining why having a super powerful, super expressive world, it's like I don't have to stare at C++ template error messages. I can be in Python, but I get the full power of the silicon and it can make people go faster and enable this research, this is what I really fall in love with. So with that, thank you. Welcome to the Modular office. It's amazing to see the folks in person, also the people that couldn't make it that are remote. We are hiring for a ton of different positions, by the way, and so if you're interested in this kind of stuff and would like to contribute, please join our community, but also if you'd like to join Modular, let us know. I think I will wrap it up and hand it back to Caroline.
Thank you so much, Chris. Let's give another hand for all of our speakers tonight. Now, we're going to get a little bit more hands-on. We're going to kick off the GPU programming workshop led by Chris Hodge, who leads developer advocacy here at Modular. So he's going to walk you through the fundamentals and help you get set up to start building your hackathon projects this weekend.
Okay, great. So let's get started. My name is Chris Hodge, and I run developer advocacy here at Modular. And we're going to go through a workshop today, and kind of walking you through kind of all of the basic information you need to know to start building kernels and models with Mojo and Max and the Modular platform. So we're going to start right at the beginning. How do you get the software installed onto your system? How do you start, set up your coding environment? Teach you a little bit about Mojo. Go into a little bit of GPU programming with it, and then we're going to turn it over to Brad, who will walk you through how to build models and how to extend PyTorch. So there should be a little bit of something for everybody in this talk. And so let's get with it. So to start off with, we have the part one is going to be the foundations, right? We're going to cover why Mojo. Once we've kind of covered the foundations of Mojo, we'll teach you how to set up with Pixi. Then an introduction to Mojo for GPU programming, hands-on GPU programming in Mojo, and create your own model, and then the PyTorch integration. Okay, and as we go through this, we have a bunch of resources that are available, and hopefully you got some emails pointing you to some of these resources before the event started. We have our open source repository where you can find all of the kernel code that we've opened up recently, all of the standard library code. Our incredible docs team has produced an introduction to GPU programming in Mojo, as well as Asan from our developer advocacy team has written GPU puzzles, which we're going to cover a little bit tonight, which will walk you step by step through hands-on experiences for how to program GPUs. We also, if you want to use AI coding assistance, we have documentation on how to set that up inside of your environment. What we found is that systems like Claude Code work great for looking at the modular repository, looking at your code, offering suggestions. I mean, at some point we've even experimented with building models from scratch with Claude Code. So we encourage you to integrate that into your projects if you have that available to you. And we have all sorts of guides to help you set that up, including like LLM.txt files and Claude.md files to walk you through this, as well as the forum at forum.modular.com, where we encourage you to go and ask questions, share anything exciting that you're working on. And at the end of the hackathon, you'll be able to share your results there with a larger community. Also, all of these slides that you see tonight we just open sourced those at the Modular GitHub repository. So if you go to the Modular/workshops repository, you'll be able to find these slides there, find all of these links, go through them yourself later if you want to. Okay, so let's get on to part one, the foundations. So why Mojo? There are lots of reasons why we built Mojo and why we think Mojo is an incredible way to program GPUs and high performance computing. The first is that it's a heterogeneous systems programming language. And what that means to us is that you can point it at almost any high performance hardware and you're going to be able to get results out of it. we've thought about building the language from the ground up with how it interacts with hardware, how you interact with the programming language to make it easier to write really fast code. Part of how we did that is by introducing a Python-like syntax. And so, like, if you have Python code, you can almost copy that over line for line, and with a few changes to help to match up to Mojo's syntax and type system, you'll be off and running, right? So you can prototype in Python, move to Mojo. We want to make it as easy as possible for you to learn a language without having to go learn C++ and memory management, or having to go learn Rust and its memory safety systems. We've also built in zero-cost abstractions. So there are ways for you to write code that at compile time can target different data types, different architectures, without you having to go and rewrite everything from scratch, right? And so we think that this is, just a powerful accelerator to help you write more code that's effective across platforms faster. We have a strong type system, so because it's a compiled language, we can check types at compile time, make sure that your code's going to run. And similarly with memory safety, C++, you have to worry about things like memory allocations, deallocations, overrunning your pointers. Here we take care of a lot of that for you, right? When you want to be memory unsafe, you can. And sometimes you need that for performance. But out of the box, we try to guarantee memory safety in a way that's easy for you to understand. So when we talk about like how did we build the language from the ground up, well, we have built-in SIMD support, right? So where most languages think about SIMD as an add-on, or you have to interact with the hardware at an assembly level to kind of access the SIMD or through libraries, SIMD is built in for any hardware that you're working on, and it's available immediately as a first-class data type. We also give you direct hardware access and cross-hardware portability in a way that doesn't require you to go and make a bunch of makefiles or a bunch of build systems. And so you can take Mojo, you can take a Mojo library and run it on your Mac. You can run it on an Intel machine. You can run it on your GPUs, right? And we wanted to be able to ship that with the same library across all the platforms, so you don't have to go and recompile for absolutely every place you want to target to, and think about how you're going to recompile for that. Okay, so with some of the fundamentals about what makes Mojo different, we want to talk a little bit about what makes GPU programming a little bit different. By raise of a hand, how many of you have programmed GPUs before? Right. Okay, so that's maybe about a little less than half the room. How many of you haven't programmed GPUs before? Right, yeah, so about the same there. So, this is, hopefully, you're going to walk away tonight, in a way, this weekend, everybody in this room will be a GPU programmer, right? And in fact, within the next 15 minutes, if you're following along, you will have programmed a GPU for the first time if you've never done it before, right? And so if you have your Lambda credits ready, you're logged in, you're ready to go, like, we're almost there. So like traditionally when you program a GPU, like there's a lot of pain points, right? CUDA is typically programmed in C++. There are new abstractions coming up to help you program CUDA and target GPUs. But the fact of the matter is that it can be complex and error prone because C++ is a difficult language to learn. Like if you look at the code here, you can see you declare pointers to ints. There is a malloc here, which you have to pass a reference to the pointer, which can be a little bit confusing if you haven't seen that before, with an allocation that is the size of the type that you want multiplied by the size of the data type. Then you have to copy that over. You can finally perform your memory add, your vector add, and then synchronize that. And then when you're done, don't forget to free all that memory that you allocated after you performed this operation. So what we've strived for with Mojo is to replace that with elegance and to replace that with expressiveness. And so we begin by getting a context, which is a simple device context. And it will find the device that is on your machine. And so if you have an NVIDIA device, it'll pick up that NVIDIA device. If you have an AMD device, it'll pick up that AMD device. In the future, pick up other GPU devices as we add more hardware support. So we do our same thing here where we allocate our memory. And so this is a context in queue create buffer with our data type and our size, right? So there's no pointers. Don't have to worry about that. You don't have to compute the actual size that you want. You just pass it the data type and the length of the data that you want for the input and output vectors. And then for the context, we enqueue a function. So we actually enqueue this vector add function, which is generalized to be able to work across any data type. That's what's happening inside of these brackets right here. And then we send in these 3 pointers. We cast them to unsafe pointers because the GPU likes that. So if you see the unsafe, don't be afraid. And we're actually working on removing these unsafe references from the code. So this is going to improve over time. And then you call context synchronize, and it'll go and run the function that you enqueued onto there. Right? And so it's more about getting the work done rather than managing the device. Okay, so coming back to some of the ergonomics that we have here, we have direct hardware access with Python ergonomics. We have built-in GPU types with device context, and another thing that we're going to show you also called a layout tensor, which actually helps to resolve even more of your memory management, both off of the GPU device and on the GPU, as well as automatic memory managed with ASAP destruction. Right. So if we go back to this slide right here. We created all this data there, but Mojo knows when these go out of scope and when they're not used anymore, and it deallocates that memory for you automatically. Right. So you don't have to think about your memory management anymore. We have performance features, so we have asynchronous operations between the CPU and GPU. It's thread safe by design so that we can achieve massive parallelism. And we have built-in compile time optimizations for peak performance. Okay, so if you haven't done this yet, this is a good time, if you're following along, to set up Mojo. And the way that we recommend that you do this for this workshop is to actually install Mojo using Pixi. Pixi is an open source package manager. It's built on top of the Conda ecosystem, and it allows you to set up kind of fully encapsulated development environments that don't interact with the rest of your system, so that you can install dependencies, you can install Mojo, you can install other Python libraries that you need to run on top of this, and it'll be guaranteed to work inside of this environment. You can guarantee the version of Python that you have. So, if you're working on a Mac and you have Homebrew and that is ships with Python 3.13, this is a good way to kind of like work around that and make sure that you have a Python 3.12 installed, which is the highest level we support right now. Compatible GPUs, Lambda everything across Lambda is going to be supported here. NVIDIA H100s and 200s, A100s and 10s. We also support AMD systems, server grade systems, and so MI300s, MI325s. But if you want to work from your own device, we support NVIDIA RTX 40 and 30 series. And I actually think this slide may be a little bit out of date. I think that we support 50 series too. 50 series also, as well as we just added support for a bunch of RDNA, I think 3 and 4 systems. And so if you're running AMD consumer GPUs, you can also run Mojo on that. Right, so check the documentation, it's changing all the time, but we're constantly expanding support. And one of the great things about this is almost all of the consumer grade GPU support was added by our community. So they're out there contributing to the standard library, adding the support and enabling this for more and more people. To install, you want to install Pixi. And then you call Pixi init quick start. You want to pass it this -c option. This tells you where the modular nightly releases are at. So we have a conda.modular.com channel with Max Nightly. And you want to point that to that channel so that you get the latest version of Mojo and Max. Yeah. If you head over to the modular GitHub and go to the workshops repository, all of these slides are stored as markdown files, and you can follow along there. Then you change into this quick start directory. You can do Pixi add Max, and then you can Pixi run Mojo, and that should give you a version. And if you're following along and you run into problems, raise your hand, and I think that Brad might be able to walk around and help you out. We also have a VS Code extension. So if you like coding in VS Code, make sure you go and download that. It adds a lot of nice affordances. But make sure that there are two versions that are in the marketplace right now. There's a stable version that will keep you up to date with the stable version of Mojo, and there's a nightly version. Make sure you grab the nightly version because we're releasing new features all of the time. And although we just had a recent stable release, and so you should be pretty close, the nightly version is going to give you better luck on the things that you're working on here. We're also working to make this extension more available for like cursor. Brad, did we get that? Okay, so we're working on uploading it. So if you're a cursor fan and you want to use this extension, it's coming soon, right? I hope maybe by this weekend, but very soon, if not then. Okay, so let's jump into an introduction to Mojo with essentials for GPU programming. And so we're going to start with an overview of the language. Okay, so we start with the core language concepts. And we do that with hello world. We have a function. So the functions are the entry point. The function main is the entry point into the program. And from there, we can print hello world. We also have, you can do things like a basic function, like function add. So we use the function keyword to declare that it's a function. We give it a name. So this first value here with the colon is the name of the variable that we pass into it. And then that's followed by a type, right? This should be familiar to a lot of you. You can have as many input variables as you want. And then you specify an output type. Indent with white space. Then you can return a plus b, right? So this should be familiar to, if you've worked with Python, a lot of this should be familiar to you. Now, one thing that might not be familiar, but that you'll see a lot of, is you see that when we define a function here, we have some square brackets. And these are there to parameterize the function. And we'll dive into a little bit deeper of what that means to parameterize the function. But essentially, it's reconfiguring the function at compile time with the parameters that you specify in here. And so, for example, this kernel takes a size, which is an integer, and a data type, which is some data type that you specify, right? And it will take as an input some sort of unsafe pointer that is also parameterized against that data type. And Mojo will compile this function down to optimize it for the particular types that you pass that you need for runtime. And a key point here is that you absolutely need to use functions when you're programming GPUs, because functions allow you to completely define what you want the function to look like, and it doesn't give you any additional stuff around it, which will be important when we talk about defines coming up next. Anything that runs on a kernel needs to be a function, right? And right now there are no exceptions to this. But we also have a Python compatible def function. So you can also def main. And one of the big things that def does is it, by default, raises exceptions. You can also pass unspecified types, and it will try to determine this at runtime, and that will come at a performance loss, right? And so these are big reasons why these are a no-no for GPUs. You know, and for GPUs, it's mainly because you can't raise on the GPU, right? And so, you know, this def main is equivalent to this function main with the raises keyword, which we use to say that this function will raise an exception. Okay, so now we know how to define functions. How do we define variables? Well, there's a Python way to do it. Just type the name of a variable equals something, and it'll figure it out. But if you want to be more specific about the variable, which is useful for type checking, then you can use the variable keyword, the var keyword. So it's a similar syntax. You use the keyword var with the name followed by a colon, followed by the type, and then an assignment. And this is the same as a shorthand for just typing a variable name, but using a type initializer to initialize this. Okay, so to recap this, there are two major types of functions. There's an fn function, which is strict and safe, has no exception by defaults, and it's absolutely required if you're writing GPU kernels. But you have def functions, which are Python compatible. They can raise exceptions. They're more flexible. They have runtime behavior, which is, you know, you can pass generic types to them, and they're interop friendly, right? We've just released a whole bunch of Python interoperability, and def just makes it easier to kind of work in the Python ecosystem. So if you're looking for types, so as you program, you're going to need to specify the types that you want to run on the GPUs. We have a whole host of types that are listed here. I won't go through all of them, but what I will call out is we once again run into the parameter system, and so you have list with the square brackets around the t, and so it's a list that contains that type t. And we see this for pointers and unsafe pointers, as well as a SIMD type, right? We talked before about Mojo knows about SIMD, and it knows about it through the SIMD type, and it's parameterized by the data type that it has and the width of the SIMD vector, right? So if you know that you have a SIMD of 128 wide on your CPU, you can specify all your data types like that, and you get SIMD operations out of the box for free. And so how does this work? You have the size of your SIMD vector. You pass your data type. You can initialize it. So we initialize it here with 4 values, and you notice that we initialize this with a float 32. And we'll show you later on like how you can perform operations on this, generic operations on this. We also have the option to do unsafe memory management. And so this is an instance where you have an unsafe pointer. If you want to do more C-style memory management, you can do this. So you create an unsafe pointer with the data type that you want, with an allocation of the size that you want, and then you can explicitly clean it up. Mojo also comes with structs. And so we don't have classes, but structs give you a lot of the affordances that you would find with classes, just with a higher performance. So you specify it with the keyword struct, specify the variables that are part of that. As with Python, you have an initialization dunder function, which outputs a self. This out is a keyword, which just specifies that this is an output type from the function. We won't go into that too much here, but we have a whole section in our Mojo docs that kind of talk about the different input types that you have. And then you can initialize it with the arguments. And then you can have functions that are members of that struct and operate on the struct. So they're, they have self-available, and they can do computations like the magnitude of this vector, right, is an operation that you could have. We also have conditional statements, and so if else, you can nest these. Loops with for and while, so these should also be familiar to you if you worked with Python. For I in range, it'll iterate over that. And a while loops, so all things that should be familiar, as well as break and continue. Now, having gone through all of these control flow features, we're going to get a little bit into CPU and GPU architecture. And one thing that you want to keep in mind when you're programming for a GPU is that while CPUs are incredible for this type of control structure, GPUs aren't. GPUs, for a bunch of different reasons, they want to run a bunch of arguments sequentially across a bunch of different threads at the same time. And introducing control structures like this will slow your processing down, right? So you want to avoid branches where you can. They're not entirely avoidable, but you want to think about that in thinking about massive parallelism rather than single-threaded computation. I also wanted to talk a little bit about compile time optimizations. So we talked about parameters a little bit before, where you have these square brackets on functions, they represent parameters, and they, at compile time, these values need to be available at compile time so that the function can be compiled to the particular parameters that you have, right? And if you've worked in C++ before, this is similar to C++ templates. And it's something that allows us to implement generics. It allows us to optimize a bunch of things. So in this instance here, we have a function repeat, which we've parameterized with a count int. So what we do for that is when we actually are inside of the loop and we have this for loop, if we put the parameter decorator in front of that for loop, that tells the compiler to unroll that loop. And it will unroll it against this value count, which has to be available at compile time, so that when you run this method repeat, instead of iterating over the CPU or the GPU 3 times to print this out, instead, if you look at the compiled code, it'll actually print hello 3 times, right? And so this is a way for you to write loops, because loops are understandable, but then if you need that to run as fast as possible, to abstract away that away at compile time, and even possibly optimize away a lot of the computation. So you're getting these compile time abstractions for free. This also works for if-else statements. You can parameterize if-else, and if this parameter is available at compile time, it'll work. And if you look at the emitted binary, only this first line will be visible. This else will have been optimized away, right? So this control branch is done at compile time. And we also have the compile time specialization. And so generics refer to functions that can act on multiple types of values, or containers that can hold multiple types of values. So SIMD is like a prime example of where this works. We have just like, a rough outline of the SIMD type here. We have a structure, which we have parameterized against our data type and our size. We have a whole bunch of like low-level MLIR stuff, as part of the implementation. But we also have operations that are supported within this, right? And so multiply is a standard operation for vector data types, to like do element-wise multiplication. And what that means is that we can specify, say, a vector, which is a SIMD of type int16 with a width of 4, initialize it with some values, perform that multiplication, and then print that out. But you could actually go back and take the same code and change this type to float 32, or to b float 16, or to int 32. And everything else would work exactly the same. And not only that, it's not this dispatch doesn't happen at runtime, and so you don't have some sort of vtable lookup performance when you do this. Instead, this is inferred at compile time, and it's compiled down, and you know that you're getting optimized code for your data types, but you didn't have to write. You don't have to write the multiplication method for every time that you implement, for every data type you want to implement this for, and you don't take a runtime penalty for doing this, right? And so this is really powerful, and is what offers just a ton of the performance for Mojo. Okay, so what are the key takeaways here? Functions are for kernels, SIMD types for vectorization and fast computation, and structs for efficient data structures. Okay, any questions as we wrap that part up? Okay, cool. So let's get on to some more implementation details. And for this, we're going to do a little bit of hands-on GPU programming with Mojo. And if you haven't done this already, you should clone the Mojo GPU puzzles. We're going to go through 3 examples from the puzzles, illustrates some of the differences between CPU programming, GPU programming, and I really encourage you to work through as many of these puzzles as you can, because it'll help you build up your how Mojo works as a language, but it'll also build up like how programming GPUs works. We have 24 of them right now that take you all the way from the most basic operations of just accessing data on the GPU, all the way to implementing high performance matrix multiplication. But let's begin by talking a little bit about what makes GPUs different from CPUs. Well, CPUs just have a few powerful cores that are optimized for sequential processing and complex decision making, right? They're great for logic, right? But they're really bad when you want to do computations on a ton of data as fast as possible. Where GPUs have thousands of smaller, simpler cores that are designed for parallel processing, but they're not so great at handling parallel logic computations, right? And so these 2 devices become complementary to one another. CPUs handle complex program flow, and GPUs handle high performance computation. But let's dig into this a little bit more deeply. So this is kind of an abstracted view of what a GPU looks like. And we're going to use some of the terminology from NVIDIA GPUs here. But a GPU has a bunch of these streaming multiprocessors, which themselves are composed of a bunch of different computational threads, as well as matrix and tensor cores that handle more advanced operations that are built to speed parallel computation. So you have streaming multiprocessors. They're self-contained processing factories that operate independently from one another. You have CUDA cores and stream processors, which are basic arithmetic units that perform the calculations. You have tensor and matrix cores, which are specialized units for matrix multiplication and other AI operations. Matrix multiplication is everywhere, and it's expensive. So if you can make it fast, a ton of computer science, even today, is still devoted to figuring out how to make matrix multiplication faster in different environments. And it's been an active area of research for decades. You have register files, which are ultra-fast storage for thread-specific data, as well as shared memory and L1 cache for low latency memory and data sharing between threads. So with the GPU execution model, you'll hear a bunch of different terminology, and it's important to understand what the terminology means. So you have grids. These grids are themselves composed of thread blocks, and then the thread blocks have a number of warps. Right? So there's this kind of hierarchical data structure that you have there. And what happens is you have a kernel that is a function that runs on top of the GPU across thousands or millions of threads. The grid is the top level organization of all of the threads that execute a kernel. And the reason why we call it a grid is because GPUs were initially designed for handling graphics, right? And so we think about it as like typically 2 by 2. We have thread blocks, which are groups of threads that can collaborate and share memory amongst one another, right? And so we've organized our grids into blocks. And then these blocks have warps, which are subsets of 32 to 64 threads that all execute the same instruction at the same time on different data, right? And these warps and how these warps work are the reason why branching logic causes performance problems on GPUs. And it's getting better with more modern GPU, more modern GPU architecture, but it's still something that is, you want to be aware of. And this is what we call single instruction, multiple thread execution model. So when you're thinking about performance, things that cause performance problems, warp divergence. You have a performance penalty when threads in a warp have to take different paths, when it has to have logic. You want to make sure that you coalesce memory, and so you want to have efficient memory access when threads access continuous locations. You want to make sure that your thread blocks are multiples over the warp size for optimal resource usage, right? So you don't want to leave threads unutilized. And one of the ways that GPUs achieve performance is through latency hiding. And so GPUs will switch between warps to hide memory access delays so that it can be loading memory while computations are happening. All right, so I promised you at the very beginning that within 15 minutes or so, you would be writing your first kernel. And this is the code for the first kernel. Once you have executed this, you have officially become a GPU programmer if you've never done it before. So let's break this code down. We import our libraries. And so we have a GPU library where you can import a block index and a thread index. And you can think of the block and thread index as unique identifiers for where your code is running at any moment on a GPU. From GPU host, we import a device context. And so this will discover the context on your device. And so if you have an NVIDIA GPU, it will bring this in. If you have an AMD GPU, it'll bring this in. It'll bring it in. And then we have a function print threads within the GPU. And this is actually something that is pretty cool. Like being able to print data from a GPU directly from the language is incredible for when you want to debug your kernels. And it's actually kind of a hard problem to solve, right? And we made sure it was right there up at the beginning because this is a great affordance to have as you write your kernels. But what this kernel does is it queries the block index and prints it out. And it queries the thread index and it prints that out at these values that we loaded up here. Then from our main, we load the device context. We enqueue that function parameterized against our print threads. And so remember that Mojo is going to do the optimization to build this kernel into the dispatch at compile time with a grid dimension and a block dimension. And so this is specifying the size of the grid and the size and the number of threads in the block. And then it'll call context synchronize to make sure that it runs the function on your GPU. And that's it. That's literally all it takes. And if you implement this and you run this, what this will do is remember that we had 2 blocks, and each block had 4 threads in it. It'll print your block index, and it'll print your thread index. And each of these pairs will be unique. Right? So we ran 8 threads of this one function. Right? And that's how you achieve parallel performance in an easy and manageable way. All right. So this brings us to the first GPU puzzle. We're gonna try to take some of these ideas and put them into practice. And so what do we have? we're going to take an input array that's going to be of size 4. We have a fun little animation here to go through this. We're going to have GPU parallel threads in a block, and so we're going to make sure that there are 4 threads available. We're going to dispatch each of these values to these threads, perform a computation where we add 10 to each of those values, and then we're going to bring them back together, and we'll output those values. So if you're following along, I recommend that you go to the code. This is just a sample of the code that's in the puzzle. But you'll notice that we do a little bit of basic bookkeeping, and so right at the top we set some aliases. Aliases are also handled at compile time, and so these are all constants that are available as parameters or for other helpful things. We define the size of the array that we're working with, the number of blocks per grid. We set the threads for a block to be equal to the size. Why this is important, why that's important will become evident later on in other puzzles, but this is, in some ways there just to make sure that our kernel doesn't blow up on us. And we set the data type that we want to work with. And we have this function add 10, where we find a thread index, right? Remember that this thread index is a kind of unique identifier. And your job is to write the function that does this mapping. And it should only take 1 line. There's more scaffolding around this as we enqueue this onto the GPU and the context, and all that code is available inside of the puzzle. Right, so we'll take a minute and give you time to fill it out, give you time to look at it before we reveal the answer. Who's finished this? Who's actually kind of like worked through some of these puzzles and has worked through some of these things? We have a few hands that are up. Okay, so if you work through it, you know the answer. You have this thread index, which you use to access the shared memory on the local memory on the GPU of the output variable, and you set it equal to the input variable at that location plus 10. And when you run this, this will add 10 to all of the input values, right? That's that easy. Okay, but there's actually I hid some complexity there because I set the number of threads equal to the width of the input vector. What if you have more threads than you have data? Which can be very common, right? If you're like, you can't guarantee that all of the data that you have is going to fill up all of the threads available on a GPU. And but you want to make sure that you allocate as much as you can. So you reach a possibility where if you indiscriminately access memory on the GPU, you might walk off of the end of the data and hit a memory allocation error. And so that's what we're teaching here. In this instance, we're going to have 8 threads on the GPU, which is twice as much data as we're sending in. And we want to do the exact same computation. We're going to do this mapping operation, but we want to do it in a way that is safe and won't cause the program to fail. And so what we're going to do is we're going to add a guard to our function. And so the function looks very similar. We have our add 10 with our inputs and our outputs. We have our thread index. And this time we want to fill in the function, but it's going to take 2 lines. So, if you think about like, what is the thing that we need to do to like prevent this, from the function from blowing up? And it's really the exact same solution. We have this output I is equal to AI plus 10. But we just add 1 check to make sure that the thread index is less than the size, right? And that way we know that we only access the data and perform the computation if the data is actually available. Right? So same computation. Okay, now we're going to skip ahead to another puzzle. And this is going to come to the idea of GPU thread blocks, right? Remember we talked earlier about how we have blocks, and this block idea comes from the idea of the graphical representation that you're trying to draw on a screen, usually with a GPU. And so blocks kind of like have XY axes, a way of thinking about them. So on this puzzle, we're going to do a mapping, but we're going to do it on a 2D square matrix A and store it in a 2D square matrix on the output. And what we want to note is that A is going to be row major. That is that the rows are stored continuously, and then the columns are stored on, that means if you want to jump. So as you move across rows, this value will be continuous to this value, be continuous to this value, but this value is not continuous with that value. And what we have here is we have a small 2x2 matrix. We're going to send that to a 9x9 block, right? So once again, we have less data than we have threads. And we're going to output that operation. So this is just a slide that kind of covers row major. And so we have puzzle 4, which again looks very much the same. This time though, we have a row and a column ID, which you get through the thread index, right? Remember that the rows the Y value corresponds to the rows, and the X value corresponds to the columns. And then once again, you want to write a way to map the memory. And this is a very traditional way. This is a very CUDA way of thinking about this. And what you should note too is that the input is actually just a single vector, right? So we're thinking about the memory as like two dimensions, but how it's being laid out in memory here is actually a one-dimensional vector, right? And so you're going to have to think about also how to map from that one-dimensional representation to the two-dimensional representation based off of where you are on the block to perform this computation. So on the solution, the first thing we do is we have our guards, and so we want to make sure we don't go out of bounds on the X or the Y direction. And so we do that by checking against the size. This is a little square by square matrix. And then we do this computation here, which tells us where we need to index our data, our one-dimensional vector in a two-dimensional sense. So every row has a particular length. That's the size. And so you take the row times the size. That tells you which row you're in. And then you add the column to index the column directly. And you do this for the input, you do it for the output, you do the mapping there, and you've solved this puzzle. And you've done it in a way that is memory safe, and it like works, according to like how the block layout works. But you think, well, wait a second, shouldn't this be like, I thought there's a lot of math here that looks like I'm doing pointer math. What am I getting that's better here? Well, we actually have an answer to that, and that's called layout tensor. And the idea is that layout tensor is a data structure that looks like a tensor. It can be a vector, it can be a matrix, it can be a three-dimensional tensor. And you get all of the things that make it easy to work with tensors, like being able to index directly into it without having to compute where the value is in the index. As seen here for 3D indexing or with padding. And it translates directly to the GPUs and handles a lot of this work for you. Right? And so you can see that like you get idiomatic access with layout tensor, as well as like much more advanced features like changing how it's laid out, column major versus row major. You can do tiling layouts, which can be used for optimizing your cache performance. You can get asynchronous transfer through all of this. And so you get a lot of helper functions, and we've included both traditional memory layout type solutions to these puzzles, but also complementary layout tensor solutions, so that you can compare the two. You can build an intuitive understanding of how GPU programming and memory management works, but then you can begin to work with the higher order affordances and be able to program a lot faster and a lot more efficiently. So how does it work? We import the layout tensor. You define a layout. And so these layouts, remember that aliases will bring things into compile time. You allocate your memory. And then you initialize the layout tensor with your data pointer and the layout that you've provided. Right? And then you can treat the tensor like, any other tensor you would find in a Python, like you would find in a NumPy or in PyTorch. Right? And the Mojo manual has a full section devoted to how you use layout tensor, and the puzzles will exercise how you use layout tensor. So let's go back to puzzle 4 with the 2D map. Yes. The fastest growing. Yeah. So in the row. Right. Right. So row major means that the columns increase one by one. Right. So if you jump if you jump a row, I always get confused by this. I always feel like I get it backwards. But it's sequential across. So as you read across the row, the data access is sequential. If you read across a column, right? If you read across a column, which means you're reading down, then you're making large memory jumps, right? So I probably got it backwards there, right? At some point. But row major means that as you traverse the column, as you traverse the X direction, memory access will be sequential. Yeah, this is why layout tensor is nice. you don't have to think about this as much. So looking at the solution here, you remove all of these computations of where the index is, and you can just assign the output directly to the row in the column, right? And this is available to you on the GPU. Yes. So the answer is yes, it should. And I think that, so it's under heavy development right now. And I know that bounds checking is a thing that is we're looking at ways to add it in. And Brad may understand some of the challenges as to why that's right. Yeah. Oh yeah, sorry. Right. Yeah. Okay. So the question is like, why doesn't layout tensor perform the bounds checking for you?
Yeah, and so like I think that like so the what I was stating is that in general for Mojo for GPU programming, right now when we have a balance between safety and performance, we're leaning towards performance. And so like whatever can get the most out of the hardware. However, there's a lot we can do at compile time. And so things like layout tensor, it does a lot for you at compile time. That's one of the beautiful things about it. And I think Chris was showing off like some of the compile time meta programming that you can do in Mojo, and layout tensor is fully enabled by that. So there are a lot of things that it will check for you at compile time. But you can do things like specify like runtime layouts that cannot be checked totally at compile time. So there are things that like you can check and cannot check. But again, we always try to lean towards give you the absolute most out of your hardware that you can get out of these.
I think you should stay up here, Brad, because I think that actually we have one more. We have one more puzzle. So we have one more puzzle to go through. Okay, so in this puzzle, we're going to talk about shared memory. Okay, so the idea is that shared memory within a block is faster to access. So this is the same puzzle, but we're going to have two blocks, and we're going to transfer data from the memory to the shared memory of the block, where we'll perform the computation, and they'll bring everything back to the input memory. Okay, so you also want to keep in mind that you have fewer threads per block than the size of A, right? And so this is important where your data has gone outside. You have more data than you have threads in the block, and so you need to start divvying that work up to new blocks. And this is how you transport the memory to those blocks, so you can do the computations and then bring everything back together, right? So for the first example, block size, data size was the same. For the second example, input size was smaller than the block size. In this case, our input size is greater than the block size. So we allocate our shared memory at the top here. We have a global index, right? And so this is a pattern that you'll see a lot. Remember when we were computing like our tensor locations before, we can also compute like a unique identifier for where we are in the memory. So you take the size of your blocks, so how many threads are in your blocks, your unique block ID, and so that computes like an offset in the memory, and then you add a thread index, which is a smaller index, right? And so this is coming back to some of the memory computations that we were doing earlier. This is kind of memory computations across the GPU and like where you are in the GPU. And I always just like to think of this global I as like the unique identifier of the thread that I'm on in relation to everything. And then we have a local thread index, which is just equal to the local, to the smaller thread index. And so if you think about this global index, that can span in this case from 0 to 8, right? Because our block size is 4 threads. But this local index is only going to span from 0 to 3, because you have your 4 threads inside of them. When I said 0 to 8, I mean 0 to 7. So you check to see if you're going to overrun the bounds of your array here, right? So this is your bounds check. And then, and so this is where you're copying your local data into the shared memory, right? And so your shared memory is smaller. And so you're taking data out of the global index, which is a wider data, and you're putting it into the shared, which is smaller. You have to wait for all of the threads to synchronize. And so the threads may do this at a different order. And so you want to make sure that all of your data is loaded in and ready to go. And then the rest of the puzzle is to fill in the computation that we've done before, right? Mapping 10 to all of the values. So once again, we have our barrier check. And then we set the output at the global index to be equal to the shared index plus 10. Right. So the way to think about this is less about performance, because why would you do this computation? But it's more to think about like the interaction between the shared memory and the global memory, right? And kind of build an intuition about how that works. Okay. And with that, that's the last example that we have from the GPU puzzles. These were all really simple, right? Up to, puzzle 8 is still doing some mapping operations. But I guarantee you that if you work through the entire set, we have 24 of them, you will build up your skills to more complex functions, and you'll finish off with writing fast matrix multiplications, which is one of the endpoints for this, and then writing fast replacement kernels for PyTorch functions. So, and with that, I'm going to hand it off to Brad, who will give you a kind of a whirlwind introduction to developing models with MAX.
All right. Thanks, Chris. So this is actually a fairly new thing that I'm going to be showing off here. And so we've just opened up a lot of this in even the last few days. And so in fact, I think we were just shipping some of this like this morning for resources to be able to support this. So you've seen so we started with Chris's introduction to Mojo. Mojo is our high performance programming language that powers all of our kernels across all of our Max models. It's the foundation on which all of this is built. But we've built a lot more on top of that. And you saw a great example of this with the AI fake Tim, where we had this full text-to-speech model that was running state-of-the-art performance, and all of that was being powered by Max. All of that was being powered by Mojo kernels under the hood, and that was a bespoke model that was built out for that specific use case. And so we have built, and we'll talk about this in a little bit here. We've built out model architectures that support pretty much the top of the most downloaded list that you see for text generation models on Hugging Face. But one of the exciting things here is we've started to just open this up so you too can build models yourself on top of Max. And so I'm going to talk about what Max is, how that's built, how our models are built, and kind of provide an introduction there. And then that's one of the themes that we're trying to emphasize as part of this this weekend hackathon, is getting people to work with this in addition to what we have already shown for Mojo GPU programming, and more that you can do with that. We have a number of resources. Again, I tried to post the links to the slides and so forth in the Discord chat. We've got a lot of active posts in the Discord chat right now. One thing I'll get to before I forget is that I've seen a few people ask in the Discord chat, if you are running the GPU puzzles and you get an error that says it can't find current architecture blank, that means that it's not detecting a GPU. And so this is what you'll hit if you try to run those right now on Apple Silicon Max, because we don't yet support Apple Silicon GPUs. And so that's why we encourage you to take advantage of those Lambda compute credits, try to be able to run those puzzles on the GPUs there. However, if you do have a compatible NVIDIA GPU, you'll easily be able to run these examples. If you do have an NVIDIA GPU and you get that same error, it probably means that something's wrong with the NVIDIA driver itself. So check NVIDIA SMI to see that the driver is okay. So just before I got into things, I was seeing that in the Discord chat. So we've got a number of resources you can get started with. A lot of these are fairly in-depth reads on, we have a lot of tutorials we have just rolled out on how to build models, how to build them from basic graphs all the way to complex models, and how to serve them. And I'll show some of the examples of that here as we're talking about it today. So when we talk about a model in Max, what do we mean? So models in Max are defined using the Max Graph API. The Max Graph API is the way that we set up models in our Max framework is we define them as computational graphs, where you define the nodes of the graph for the computation that defines what the model is. This is in contrast to something like PyTorch, where you may have defined a model where you have eager execution at each step. This may be familiar to those of you that remember TensorFlow. And it defined models in terms of graphs. So we define models in terms of graphs because this gives us unique advantages for being able to compile and optimize those graphs to get the most performance. We build them using the Max Graph API, which we'll talk about in a little bit. And we define them in Python. And again, I'll talk about this in a little bit here. It may seem confusing because we were just talking about a whole bunch about Mojo. Why are we talking about this in Python? But that gives us certain advantages for being able to build these models out, integrate them into the ML ecosystem. And again, I'll talk a little bit more about that. But it's a very familiar interface. It should be a familiar environment for you to work on for building models. And as I mentioned, these are staged as they're tensor computation graphs. And even though we're talking about building these models in Python, every single node in that computational graph is a Mojo kernel. And in fact, all of those Mojo kernels are in open source today. And so you can go and you can look at the Mojo code for every one of those. Oh, and I'll also mention all of our model architectures are in open source, and our graph API is in open source.
So we posted the link for our open source repository earlier. You can see pretty much everything that I'm going to be talking about here. So like we just spent a while talking about Mojo for being able to build high performance compute kernels. Why build the Max Graph framework in Python? Well, it, like, as we say here, it provides the best of both worlds. So Python is the language for ML today. Massive code bases, huge serving infrastructures, everything built on that. And so, you know, we realize that we want to meet ML developers where they are. Like it's one of the core missions. It's why, you know, Mojo has a very Python-like syntax. It's, you know, it's that familiarity in the AI developer ecosystem towards Python. So we have built the Max Graph API in Python so they can directly integrate with your existing, you know, Python code bases that you have today. It provides seamless interoperability with things like NumPy arrays, PyTorch tensors. We'll even talk a little bit more about PyTorch integration later on. So you don't have to rewrite the world to have to use our high performance Max graphs. You can start progressively integrating this into your existing ML ecosystem. And you know, just Python is everybody, like, it's a super familiar language. It is very easy to work with, very easy to iterate on. And, you know, in terms of, like, we were talking about the performance advantages of Mojo, when you're talking about things like building ML graphs like this, your computation time is dominated by the execution time of running the graph itself. And the overhead from a host language in Python is generally minimal. We don't talk about it here. We also have a solution for that too, where you can now progressively replace Python with Fast Mojo using our new Python to Mojo interoperability, which we don't talk about in this talk. I'm glad to talk more about it if you're interested in it. We hope to see that as like a solution for progressively replacing even the slower portions of Python code with Fast Mojo. So it's very easy to actually, like, you can try out, as I said, we have model architectures that support 500 plus of the most popular LLMs on the market today. Things from, like, you know, Llama to Qwen 2 to others. And you can try them out today running, like, again, with our optimized pipelines, with our optimized Mojo kernels across multiple hardware platforms using very simple invocations. We have, if you install our full modular package, you'll get a command called MAX, which is basically just a wrapper around our max.entrypoints.pipelines Python module. And it has a few different options, one of which is to say serve. And all you need to do is say serve and then point it to a Hugging Face repo ID. That is enough. It will go out to that Hugging Face repository. It'll grab the configuration. It'll grab the architecture. It'll grab the weights. And it will fully configure a Max model for you, compile it, optimize it, run it, serve it, and you get yourself an OpenAI API compatible endpoint in one command. And that can, again, work with, like, quantized models. It can work with a wide range of different model formats. And also, like, you can, again, you can invoke this directly from the max.entrypoints.pipelines module itself via Python. If you have, like, say, a Pixi environment where you've installed Max and you want to hack on the Python source. Again, all of the source code for all the models that I'll be talking about will be on our main repository. You can also do like quick kick the tires tests on, like, just having a model just do straight text generation using just the generate command. This is often great for doing iterations on model architectures where you just want to verify that it is running, that it is compiling, that is working all the way through without having to stand up the full serving system. And so that's a great way to, like, just go and try things out. So Max Graphs as a whole, we have a number of different modules for going and building them at different levels. We have the core graph abstraction in max.graph. That is, you know, where you define a graph, you stage it, you work with it. We have graph operations, which we'll talk about in a little bit. These are the atomic operations by which you build your graph. That's in max.graph.ops. Again, all these are covered fully in if you go to docs.modular.com, you can go see our full API documentation across all of these different areas, search through, find them, see the full list of all the different interfaces for all of these. The max.driver. So when dealing with accelerators, host device transfers, setting up tensors, All of that is handled through the max.driver interface. That lets you work with CPUs, GPUs, even multi-GPUs. You can go and set up and transfer data directly from GPU to GPU using the max.driver interface. Makes it very easy, again, very easy Python interface for going and accessing host and accelerator devices. And then we have our inference sessions, which when you have a graph, you compile it down and you run it via an inference session. I think we'll show a little bit of an example of that later on. So building a computational graph, we use to do so, we use a Python context manager. So we can say, like, with graph as graph, we give it the graph a name. It has inputs. You're gonna have like arbitrary numbers of inputs, outputs, and then from those inputs, it's very easy to go and in this case, like, we're taking in 2 tensors. We're staging an add operation, and then providing the output. What this is doing is it is describing the graph. It is not, again, we're not running this eagerly. So it's not like PyTorch where like each operation will run in sequence. This is defining a graph. This is staging the graph, which will then be compiled and then run. We also use like ops.add here just to be a little bit more explicit about what's happening. We're using the add operation for adding these 2 tensors together. But you could just as easily do LHS plus RHS. And that will like go and also enqueue an add operation when dealing with these tensor values. So again, very straightforward Python-like syntax for defining these computational graphs. So once you've defined a graph, you need to compile it. So we have a very powerful graph compiler as part of Max. And so in addition to having a language compiler, we have a graph compiler. The graph compiler does a lot of optimizations, such as, like, most popular, like operation fusion. So you have like series of element-wise operations. It can fuse those in there. If you have a matrix multiplication with an element-wise, it can fuse. So it does very intelligent fusion to get the most out of the definition of your graph itself. So to do that compilation, you set up an inference session, and then you load the graph into that inference session. That will do the compilation of the graph. Now, it doesn't compile every single time. It'll do the compilation once for given shapes of inputs and outputs, and then it will cache that graph, and it'll cache it transparently for you. So the next time you run it through, you don't incur the cost of compiling the graph. And so it's like we try to be very good with the caching. Usually, like, it'll trigger a cache miss on like significant changes to the graph itself, changes the operations, and so forth. And if you run into problems with the graph caching, let us know. We're always trying to like refine the heuristics around this. Once you have a compiled graph, you can then execute that graph on inputs. And so here we provide like A and B tensors into this. We extract just the single output that we want from the output. And as you can see, like, we're using a max tensor here, and we can just say 2 numpy, and we suddenly get a numpy array. And it's 0 copy interoperability with numpy to and from numpy. And so we can right away get a numpy array, and you can just work with it as a numpy array. So very simple, very straightforward. It handles all that compilation, all that optimization for you behind the scenes. So you construct a graph using these graph operations, and the operations we have put together are like we think of them as atomic operations. They are much lower level than you'd find for like kernels in other frameworks. Because of this fusing graph compiler that we have, is that you can define things very simply and then fuse it together into an optimal graph. But you can also define very complex operations out of this. You can write entire custom Mojo operations yourself that cover all the way things from like a flash attention operation. So from simple to complex. But we start with the simple operations, and we have a library of these. I think it's like 200 or so operations. Again, all of the source code for the Mojo operations themselves, the things that perform the computation, is fully open source. We recently open sourced all of that. It's hundreds of thousands of lines of code. Go read through it. You want to see some fascinating architecture-specific optimizations. Go read through that. But over the last week, we also just open sourced the Python graph API. So the Python interfaces that call these specific graph operations, as well as all unit tests and integration tests. So you want to see how these operations actually work, actually are tested. All of that source code is fully available now on our GitHub repository. And so you can pick from all of these operations to go and build your graph. But I'll talk a little bit a little bit later about what if my operation that I want to do is not on that list. What do I do? In addition to the atomic operations, we've started to build an abstraction or a layering called max.nn, where we started to build like standard like layer primitives, and we're largely patterning these after PyTorch. So things like NN linear, NN embedding, like we're trying to match the conventions of PyTorch while under the hood using Max and its graph-based, computation, Mojo kernels, and so forth, to provide a familiar environment for everybody who's used to working with PyTorch to bring models to Max. In fact, at the very bottom, I linked to this is a guide we just released this morning. It's an introductory translation guide to translate from common PyTorch layers and common PyTorch patterns to Max. And so we've provided that guide as well. But again, this is an area that is rapidly expanding. We have built the fundamental atomic operations that we have in graphs. We're now looking to build that next layer of abstractions to help, largely to help the porting of models from PyTorch to Max to make it that much easier to bring in new models. But as I said, you're not limited to the operations that we've already defined for you, the ones that are already present in the max.graph.ops package itself. You can bring your own custom operations to your own model. And so you define those custom operations in Mojo. Mojo is our high performance computing language. You saw how to use it to program and target GPUs, all the way down to full use of tensor cores and all the hardware that you have access to. And so those are defined in Mojo. And so here we have a simple definition of one of these custom operations. Most of this definition here is just telling the graph compiler what is the shape of this operation, like how many inputs does it have, what are those inputs, what are the outputs, are there any compile time parameters that you want to specify in here to specialize this for a specific use case or hardware or so forth. And then the body of the operation contains what is actually done on those tensors, and that's full. You can do anything you want to. You can in Mojo inside of one of these custom operations, and so you can do some incredibly complex operations in here. So you can set up one of these custom operations yourself in your own local project, register it with the graph compiler, and then use it as if it's a native operation inside of Max itself. And you'll see that we use the exact same interface you see here for defining all of our own kernels that we have inside of the Max framework. So this is how we write the kernels that go into Max themselves. And so then once you've defined a Mojo custom operation, to use that custom operation within a Python graph, we have an example here where we use the ops.custom operator and assign and say what the name is of the Mojo, the compiled Mojo operation is that we're using, and then provide what the inputs are, outputs are for that. And we're actually pulling that from a specific kernel library where you don't have to pre-compile the Mojo file before using this. You just run this Python file. It will automatically invoke the Mojo compiler for you, build your operation, then be able to expose that operation to the graph compiler for use. So again, try to be as transparent as possible. Try to make you not have to worry about any parts of the build system or anything like that. You just write the Mojo file, you write the Python file, and you can go. So all of these flow up into entire model architectures. And as I said before, we've built a range of common LLM architectures, the Llama architecture, the Qwen, so forth. And those are present in open source in our modular repository under Max Pipelines architectures. You'll be able to see the architectures that are there are patterned after or matching against Hugging Face architecture classes. So, like Llama for causal LM. And so anytime that you go and you load a Hugging Face model that's Llama for causal LM, it'll match against that in our Max architectures, use that architecture, populate it from the hyperparameters that are defined in config.json and Hugging Face, and build out the whole rest and run the whole model. So This is how we're able to support broad classes of the most common LLMs that are out there, is standing up architectures for each one of these architecture types. So that's why, like, check the list of architectures we've built out. It may already be there for the model that you're working with. You can also check, if you go to builds.modular.com, we have a full interactive list of the models that we support, some examples of that. So you can also see the architectures listed there that are supported within Max. But one of the exciting things we've just opened up is you now have the ability to bring your own custom model architectures and serve those within the full Max ecosystem. Where again, you get the full advantage of all of our hyper-optimized Mojo kernels. You have our serving infrastructure. You're able to stand up and serve a full OpenAI serving endpoint, and eventually it will flow up into like things like our advanced cluster solutions, Mammoth and others that I think we've talked about briefly in some of our recent videos. You get all of that within the modular ecosystem. To be able to register and serve a model architecture, we have a brand new tutorial that Patrick just wrote, and it's fantastic. We validated it through Claude Code, so I'll talk about it a little bit. Fun story, like we actually pointed Claude Code at the tutorial and said, follow this tutorial and stand up an architecture, and autonomously it was able to go and build an entire Max architecture and run it. It's kind of amazing. It is a science fiction world we live in. But the steps for registering a model architecture are, like, you build out the model graph. And again, you don't necessarily have to do this entirely from scratch. You can work from a number of templates. You look at our Llama for causal LM, look at our Quen for causal LM model architectures, and see if you have a model variant that is very close to those, start with one of those and start hacking on it and modify it. And we have, like I said, we have a lot of max.nn primitives you can go and build these out from. And so there are plenty of places to start from there. Now, as you get further away from that, yeah, there may be some things you need to build out, but that's where it gets really exciting about getting into building. We'd love to see people building diffusion models on top of Max, and it may require some custom operations. It may require some custom layers, but we'd love to see people try that. Once you have the main model graph implemented, you add the functionality for handling model configuration metadata. So like if you're dealing with a Hugging Face model, Hugging Face models have config.jsons. They contain a ton of metadata about the model layers and the heads and the attention and so forth. We read all of that. And so we provide adapters to translate from that config.json to the things that are understood by Max to build up the models. You have to define a weight mapping. So each one of these Hugging Face repositories that have weights, the names in those weights may not exactly match the names in your layers. So you can define a mapping dictionary to go and map between the Hugging Face weights to the ones that are used inside of your own architecture. And then finally, you register the architecture with Max. Say this is the architecture that is used for this name. And then when that name is looked up in Hugging Face, it'll go and use your architecture instead. Then finally, to be able to serve it, just use the -- custom architectures and point it to the directory that contains your Python files for this architecture. Again, this is all brand new. We just launched a lot of this over the last week or so. So I'm really excited to see people try this out as part of the hackathon, as part of continuing to work on things. This is where we're really excited to see if people can build out more model architectures, expand the range of model architectures that we have in Max, and we're really excited about being able to take those in and expand the community of things that are supported by Max. So, I talked a little bit about our Python interoperability. We have a very new feature that we've been just talking about lately that is all available in the nightlies out there, and that is the ability to define PyTorch custom operators using Mojo. And the great thing with this is that you get to work with Mojo. It has that cross-platform capability, working across multiple architectures. But you have the rest of it is your familiar PyTorch workflow. So you can if you just want to tinker with Mojo for a custom kernel, you can have the whole rest of your PyTorch model and then work on just replacing that one layer that you want to tinker with. Or you have all your input defined in PyTorch already, and you want to experiment with a new model, with a new attention layer or something like that in Mojo. You can do that. You can now integrate that into PyTorch. And The real nice thing about that is you saw that code that I was showing for custom operations in Max. It's copy and paste to bring that into custom operators in PyTorch. It's the same definition, the same code. You can literally copy and paste between Max and PyTorch to be able to use that. To work with it in PyTorch, we have a max.torch package that has a custom op library. And all you have to do is point that custom op library at wherever you have your Mojo source code for your custom operations. And then, at the time that it is used by PyTorch, again, the Mojo compiler will be transparently invoked for you. It will compile your Mojo files. It will then register those with PyTorch, and then PyTorch can just use your Mojo custom operation. Makes it very easy for you to try it out. Brand new thing that we're testing out. So after all that, you saw like Chris was showing you some introductory examples about how to get up and going with GPU programming. We've seen some graph examples. If you want to get into like custom operations or working with custom operations in PyTorch, we have some later puzzles in the GPU puzzle series that cover those topics as well. And the last thing I'll talk about here before I let people like get hacking on things is using AI coding agents with Max and Mojo. And this is actually a fairly new thing. Like I'll admit, I was a huge skeptic about being able to use AI coding tools to generate code, especially for something as new as Max and Mojo. Like Max and Mojo are rapidly evolving. Mojo is a brand new language. Like there's, the training data isn't anywhere near as huge as a stable language like Python that has huge amounts of code out there. But these latest AI coding agents are absolutely amazing if you give them the right context. And so, for example, we've done a lot of work internally evaluating things like Cursor and Windsurf and Claude Code, and found like some best practices for like making them work even against like a challenging environment like with dealing like Mojo and Max. For one thing, we've provided some very helpful rules. So in our open source modular repository, we have Claude.mds, which provide great context for Claude code. So if you clone our modular repo and you just like fire up Claude at the command line inside of that repository, it will start itself with great context as to here's what's in the repository. Here are our best resources for dealing with Mojo, for Max, guides for dealing with building up new models. So if you want to hack on kernels, I hugely recommend that. Like just clone the repository, fire up Claude within that repository, and then say I want to add a new kernel for this, and it'll know where to place it inside of the repository there. It's amazing what it can do. In addition to that, I also recommend pointing to, we have an LLMs.txt. So we have a using AI coding assistance guide on our website. It has links to the LLMs.txt for a variety of our different subsets of our documentation. That'll provide the documentation context to these agents. And if you're working on an external project, I still recommend cloning our modular repository and pointing the agent to that repository. Say like, hey, use this as a reference for like best practices for Mojo, for Max, for building models. Like I'll say, like anecdotally, I've been incredibly impressed. Like working with like Claude Code recently, it's been able to do things like one-shot generate GPU functions for, I said like do the Julia set fractal and have it be called from Python. No human intervention, did it work the first time. And even things like as advanced as models, what we're trying to do is we're trying to get it so that it can, given like a Hugging Face repository identifier, like a reference to say transformers, and one of the reasons why we created this guide, the map from PyTorch to Max, pointed to a guide like that and say, all right, translate one of these existing model architectures to Max. And we're getting close to it being able to do something even that complex autonomously. And so like it's a huge enabler. I've been greatly impressed by what you can do, but you do have to, again, provide the right context, provide the right guidance for these agents. I've been talking a lot about Claude, but like Cursor also, we provided good Cursor rules within our repository to help work within that. A lot of people work with Cursor very well against the modular repository. This is a lesson we learned from our last hackathon, is that I watched tons and tons of people do a lot in a single day with the assistance of these agents. So that's a lot of, like, again, you know, we've talked a lot about, you know, Mojo and its ability to build to do GPU programming, and the brand new section here is being able to build out models in Max, which, again, this is like for the first time we're kind of unveiling that for everybody to build these models, to work on them. We're super excited for what you're working on. I've seen some great ideas already so far discussed in the Discord. So, like, for those of you hanging out the rest of tonight, like, look for somebody in a modular shirt. We can help you if you have questions. We can answer that. Otherwise, like, you know, online here throughout the weekend, ask questions in the Discord. Check with them on the forums, and all of us would love to help you out. So, thanks a lot for the technical portion. I can probably hand you back to Caroline for closing statements.
Thank you so much, Brad. Let's give another big round of applause for Brad and Chris. Huge thank you to everyone who stuck with us tonight through the full program, whether you're here in person or tuning in virtually. And that officially wraps up this evening's formal programming, but this space will be open until 10 p.m. So feel free to hang out, meet other folks to work on your hackathon projects with, and, you know, start working on those project ideas for the hackathon. So we're really excited to see what you build this weekend. Thank you again, and happy hacking.